All right, so now in this video, we're going to continue with probability functions. We're going to continue with probability functions. Whiteboard. All right, so remember back in one of the previous videos, the probability of any value of x will be a number between 0 and 1. So the probability of number being, or probability of x is going to be between 0 and 1. And the sum of all possible values of x, so all mutually exclusive and exhaustive events, all possible values of x, so this could be x1 plus probability of x2 plus all the way to the probability of n. If this is mutually exclusive and exhaustive, so all possible outcomes of x is going to be equal to 1. If this is not true, then it's not a probability function. So and also notice that now we're using a little x instead of a capital X. So a capital X is going to be the random variable with some distribution. So we're going to say x is our random variable with some distribution, and it will follow, let's just give it x for now, or function of x. And maybe f of x could be, let's say if it's x1, it's going to be probability of x1. This would go all the way down to xn. As long as this covers all possible outcomes and it's mutually exclusive and exhaustive, and the sum of all of these probabilities of x's has to be 1. If not, then it's not a probability distribution. So this would be a PF if it's discrete. So this would be a probability function. And you also have a cumulative distribution function, a CDF, which gives a cumulative probability. So for a CDF, cumulative distribution function gives the probability that a random variable x is less or equal to a particular value. So before we had little f, we have a little f, which is for a probability function. Big F is going to be for a CDF. So a cumulative probability function, or a cumulative distribution function. So CDF, cumulative distribution function, gives a probability that a random variable is less or equal to a particular value. So if I say the probability of, let's say the probability of K, or let's say of CDF of K, this is going to be the probability of X being equal to or less than K. So if, back at the car lot example, if we want to know the probability, the probability of having 5 cars or less sold in a given month, then we would say, we could say big F of, so the CDF, or distribution, CDF of 5, so big F of 5. This would be the probability of X being equal to or less than 5, which would be the probability of 0 cars being sold, plus the probability of 1 car being sold, plus all the way to 5 cars being sold in that given time frame. This is discrete. It's countable. And notice that for this right here is the probability of X being equal to or less than 5. If I wanted to know the probability of X being, let's say, greater than 5, what would that be? That would be the probability of X being greater than 5. I can't do a CDF. So this, for the CDF, this is a probability. This is probabilities, and these are my X's. Say this is 0. This is the probability of X being 0. Maybe this is the probability of X being 1, being 2. Maybe it looks something like this. The CDF, so this would be our little f, our probability function. The cumulative function of X will look like this. It's cumulative probabilities, and it's going to go start at 0, or start at a low number, start at 0, and it's going to go to 1, because it can't be greater than 1. So if I do a CDF of this, I have to do 1 minus that. So if I wanted, let's say instead of 5, let's do 6. So let's say we want to know the probability of having equal to or greater than 6. This would mean that we would have to do 1 minus the probability of X being less than 6. Remember, this is countable. You can't have 5.7. You can't have 5.2. You can't have 3.14 many customers or many cars sold. It's countable. It has to be discrete. So you can't have less than 6 would be the same as a probability of X being equal to or less than 5. Now this, you can use the CDF. So now you would be able to use a computer or a distribution table to solve for it. But also notice that this is for a discrete. This is countable. Countable. So if you're trying to do continuous, something like portfolio returns, that's a little bit different. So if you're doing a continuous random variables, so something like portfolio returns, and if we do, let's say F being K, so maybe this is the probability of maybe our portfolio returns being equal to or less than K. Maybe K could be 2% or something like that. Now you have to, you can't count. You can't just count all of the possible outcomes. It's not, you can't count up all of the 0.01, 0.001, and all of that. It's not countable. So you'd have to integrate. You don't have to integrate anything in this class, but this is how you do it. So you go from negative infinity all the way to K. It has some distribution function. You integrate it, and now this would give you the probability. Let's say something else. Let's say time. Back at the car lot example, let's say you want to know the probability that someone will be in the car lot for 30 minutes or less. This would be the probability of someone being in the car lot for 30 minutes or less. You can't have negative time. You can have negative returns, but you can't have negative time. So you start at 0 and you go to 30. This is going to be some, it's going to have some distribution, and then you would solve for this, and that would give you the probability of having 30 minutes, that person being there for 30 minutes or less. So this is, this would be finding a probability of a continuous random variable. So for continuous, for discrete, you can add. So this is important for discrete. You can add and use sums. For continuous, you integrate. You don't have to integrate in this class. Anything that is continuous, even things that are discrete, we're going to use the computer to solve for it. So you don't have to do it. But this is still important to understand. And then probability theory and statistics, a collection of random variables. This is also important. A collection of random variables is independent, and identically distributed. And identically distributed. And this is called a IID. So if each random variable has the probability distribution as the others and all are independent, then it's there's a lot of things you can do with it. So this is very important in probability and statistics, and it's a very important underlying assumption in almost everything we do throughout the rest of this class. So the concept of IID is very important. So something like, I'd say we have maybe X many people coming into our car lot, and it's X is our IID, and they have some distribution with the mean, mu, and some variance. This would be an important assumption that we can then create probability models or statistical models to model it. And this assumption of IID is also real important for a central limit theorem. So central limit theorem is something you should already know. We're going to talk about it a little bit. We're not going to get into any of the proofs, but it's something that that's important. So this is CLT, central limit theorem. It's important for regressions and time series and hypothesis testing, all of that. We don't directly show it, but it's, again, also important. But both of these are important. So independent, identically distributed, especially in central limit theorem. This is really all we'll cover in this video. This sums up probability distributions. There's a lot more that we'll do later on this, especially when we get to special distributions, a little bit of simulation, and we talk about some of these concepts again, even in regression analysis. But this is all we'll do in this video.